Okay, let's wait a couple of more minutes, eventually for more people to join, and we will start promptly. Okay, so let's start. Welcome everybody to today's webinar of the Brain-Computer Interface and Neural Engineering Lab at the University of Essex. Today it's the first and only maybe hybrid event. So we are here at Culture Campus and also streaming through Zoom. And we have the great pleasure to introduce Professor Damien Coyle of the University of Bath. I will just give a short bio before the talk. Damien Coyle is Professor of Neurotechnology, a UKRI Turing AI Acceleration Fellow, and Director of the Bath Institute for the Augmented Human at the University of Bath. His research focuses on developing AI to address challenges associated with translating electrophysiological signals into control signals for brain-computer interface-based neurotechnology and trialing neurotechnology on a large scale with patients and end users, including spinal injury, stroke, disorders of consciousness, and post-traumatic stress disorder. He's also a founder and CEO of NeuroCONCISE Ltd, an award-winning AI-enabled wearable neurotechnology company. I'm sure most of you were already aware of that. So with no further delay, Damien, you can start your talk. Thank you.
Thank you, Simi. Delighted to be here in this very prominent part of the world for non-invasive brain-computer interfaces. So yeah, really appreciate the invite to talk. I hope I can provide some information to you guys today. So I'm going to cover quite a number of areas, but obviously it's going to be on brain-computer interfaces and neurotechnology, or BCIs, and I'm going to kind of cover applications that I've worked on over the last while, but bring in some of the methodology, obviously, and the results that these applications have and the impact that they've had on the end users. So we'll focus a little bit around spinal injury, disorders of consciousness after brain injury, stroke, and if I have time, a little bit on PTSD. So I'm very much focused on, see if I can reduce this down. Still there, isn't it? So I'm very much focused on non-invasive brain-computer interfaces, EEG, so electroencephalography-based BCIs, and we know that they involve modulation of brain activity intentionally in one kind of embodiment of a BCI, and then other ones that focus on stimulus-based paradigms. And I think it was Dennis McFarland that said that the BCIs is a learned skill, not simply a matter of mind reading. And he was referring to some of your work in that from the Cybathlon in 2016. And I want to kind of show that that is quite important, that we have machine learning and AI to translate signals into control signals or whatever. We have the training of the user, which is equally as important. So how much time does the user spend engaging their brain to perform a task? And then obviously the application, how do we encourage people to spend time doing this with motivational applications or applications that the person might benefit from in terms of quality of life improvements and so on. I'm going to focus a lot on motor imagery, and I'm not going to go into the details of motor imagery here, but we know it's very well defined spatially and spectrally in terms of where things are modulated when we perform movement or movement imagination. It's normally, lateralized differences give us an advantage in terms of discriminating between left and right, and the actual location of these things. So we also know that motor cortex at rest is kind of correlated with mu rhythm, and when we perform movement, we get desynchronizations of those rhythms. So a lot is known about it. Still doesn't make it easy, but it's a good task to perform, and it's also one of the most popular in brain-computer interfaces over the last 20 years. It's also a skill that you can develop, so you can get better at modulating your motor cortex and intentionally controlling signals. So that's an important factor, that we can get better at doing this over time. And then it links to our normal peripheral pathways as well. So even though we know all that spatially and spectrally, we still have to do a lot of signal processing, and we put that into a multi-stage signal processing framework. I'm not going to explain this here, but typically we need to do multiple manipulations of the data to try and maximize separability and produce a reliable classifier output. And sometimes we provide a binary output, or we provide a control signal that looks like that there, where we have a task to perform, we imagine movement, and then the classifier produces a signal that goes greater than 0 for one task and less than 0 for another task. And this is kind of that kind of thing in action here. So you can see that this is a 32 channel setup, and this is the control signal that I mentioned here, fluctuating between 1 and -1, and that's linked to the character, and the character moves from left to right based on the user's modulation of brain activity. And the focus here is to pick up the spikes as they come up the axons in this game, and by imagining left to right arm movement. And interestingly, you get points for picking up the spikes, you get points for moving towards the spikes. So it's a bit motivational, and we can collect data in this game as well, so we can improve the algorithm as the player develops or interacts with the game. Here's another application of that, where we have, and this is inspired by some work John Gann did here with a guy called Dr. Tang. That must be 15 years ago, but they did have a circle time type controller. So we've extended that now to gameplay here, where you just have 2 motor imagery tasks, but you can get 6 different commands. If you can time it right, get the bar over the threshold as time goes on. And this is much more challenging, but it also is much more entertaining. When people play this, they get really excited and they want to be the best. And you can do 2-player mode and kind of have fighting scenes and so on. So this is quite important. It's also a bit weird sometimes. But typically in a motor imagery paradigm, we'll ask people to repetitively do left or right arm movement, and we'll look at the accuracy then in terms of how we discriminate between that. And we might slide a window along the trial across, if we've got 100 trials, 50 left, 50 rights, and we want to really look at the accuracy here in the baseline period, and then look at the accuracy at every point as we move along the trial. And you can see that in this particular participant, there's a peak that happens around 5 seconds that corresponds to changes in this kind of higher frequency components. And that's what we want to see, and that's a guarantee that person is engaging in the task. We also want to make sure that it's significantly above baseline in certain applications, and it's significantly above a permutation test where we randomize the labels. just to show that there is a significant response, because this is a nice kind of curve here, but often it's a lot more noisier than that, and it doesn't really show the same. And so that's what we have to do. And we can also, if we want to do binary classification, we have to have maybe thresholds and distance thresholds and times thresholds on the classifier output to enable us to establish whether that person really said yes or really said no, or whether they want to do one command or the other. And that nice control signal that I just showed you is not often always the case either. This is what it looks like over time. So you can see here's like the square wave kind of says, right, do left for a few seconds, then do no control, then right, and then no control again. And you can see the green thing kind of follows that, but it's got bias to one of the classes over time. It's got a lot of outliers and a lot of spikes. And so we have to do things like statistical smoothing, debiasing, and then maybe adaptive thresholding if we wanted to create this discrete signal at the end. And so that means we have to do a lot of pre-processing and then a lot of post-processing just to try and get a stable signal. And that's the whole process in the We know if I put a headset on any individual today that you're probably going to hit around 60–70% accuracy if we're lucky. And then tomorrow you might get a little bit better and you might not either. But the idea is that you get better over time, and that's what we want to try and achieve in motor imagery type feedback paradigms. And feedback is quite important. So I showed you games there and so on, but as you learn to grasp a toy as a child, you needed the visual and the tactile feedback. In a brain-computer interface, it's the exact same. We need feedback. But sometimes the visual channel isn't available, or we don't know if the person can see, and so we need other types of feedback. So we've been using this amplitude panning, where you kind of move sounds from left to right in a kind of stereo panning scenario. And we start off with pink noise because that's easy to localize in space, and then we move on to musical genres, and I'll talk a little bit more about that after. So we know that BCIs have been associated with many different kind of applications in assistive and augmentative communication technology. And here's just a few. And so I'll just talk about spinal cord injury applications in the context of competing at Cybathlon. I think everybody in Bristol or in Essex is aware of Cybathlon because there's been a long history of competing at Cybathlon, either from people here now or people in the past, with Anna having won in 2016 or came third in 2016, and Simi's here having won in 2016. So I don't have to explain the challenges to you too much, but it is a very important kind of event that kind of drives innovation as far as I can see, and certainly has made us try to think about all the challenges and so on. But it's got 6 different events, more now in more recent years, and you have to basically steer this vehicle down the racetrack, performing one motor imagery to move it left, one for right, and then one for turn on the lights. And there's also a no control state there, which is nearly as difficult to do as the actual action states. And so what we did in our 2016 and 2019 and 2020 kind of thing was have 3 classifiers, or 4 classifiers, left versus right, left versus feet versus right, and pass versus relax. And these were all filter bank CSP with LDA. And so you wanted to then decide which classifier was giving you the right output. So you kind of a majority vote here. So if the left versus right was saying it was left, and the left versus feet was saying it was left, then you would assume that was left. But we also wanted to make sure that it was definitely a task situation, because sometimes you can get random fluctuations. And so the task versus relax classifier would also have to say task. And when this condition is met, then they have to be above a threshold for a certain length of time. So you have a time threshold, and then you have to make sure you're not interrupting the good command as well, so that you don't break out of the command. So lots of kind of control kind of things there that enabled us to do that. And yeah, it's all done in Simulink. And so what we found with this setup was that over time, from training up to 2019, that the race times went down. So the objective was to improve race times, and yeah, we were able to do that right up to the competition day, and then we dramatically failed on competition days on both 2019 and 2020. So very disappointing to be achieving such good race times and then not performing your best on the competition day. And we kind of tried to, think why this was the case and put it down to, some kind of arousal or, anxiety of the pilot. He blamed us, the engineers, but we were kind of trying to say, look, that this, and we should be able to deal with any non-stationarities, and that's, so he's right to blame us as well. But from then on, we got people involved in sports psychology and gave them some breathing techniques, and I think that paid off in the latter years. So in 2024, this became much more difficult. There was 4 different tasks basically. One was to drive a windshield through a virtual environment, move a coffee cup in a coffee machine, and yeah, put a key in a keyhole and select from a menu option. And so we were thinking, how are we going to manage this? There's lots of different things to do here. And on top of that, we had 4 classifiers. So we said we want to simplify this and just use one classifier and then create a kind of controller like this. So the classifier would be able to select any command, and then you can adjust the parameters of the game to do certain rotations automatically, but you have to be able to select them. So there's a lot of options and control for that. And we were going to go rest versus task, but rest versus task is nearly more difficult to manage and keep stationary than task versus task. So in this scenario, they just had to do a right motor imagery to select, get it above this threshold, stop with the circle rotating, and that will do the command. In the no control state, they did left motor imagery. So it was a bit more onerous on the pilot because they had to do tasks all the time, but it was much more stable to keep it in left motor imagery whilst you didn't want any tasks happening. So I think that was a good strategy. And like that was lots, so it became kind of just a simple BCI, but lots of other control stuff to manage, which is another task in itself. So I'm not going to go into them parameters. So yeah, this is kind of an example of those in action there. So you can see once they get above the threshold, the timing is quite important here. The speed of that circle rotating is quite important. When you decide a threshold is met is quite important. Gain or scaling the TSD or the time variance. There's lots of different things, parameters to be tuned there. And another thing is that the controller wasn't allowed on the screen. You have to have a separate controller for that. So that was another bit of a challenge to address. So this was the challenge in 2024. Don't worry about the green one, but that was the rotation speed. It was rotating every 6 seconds. So you can see there's improvement over time. And then on the competition day, which was the challenges event, we got three of the tasks completed. Sorry, this is the number of tasks completed. You have to do 6 to 8 tasks depending on what competition. And so you can see that we did 3 in the first round of the competition and then 4 in the second. And the Italian team did exactly the same, 3 and 4. However, we were faster at doing our 4th. So we won that time. It was good. After 8 years of competing, we finally won something, right? So it was a good experience for the athlete. And then we went to Zurich in 2024, and again, we started to change the rotation speed, change other parameters that are here. And you can see that we were starting to hit seven games within the event, and but it was quite variable as well. You go from 7 completions to 3, and unfortunately we didn't have the 7s in the competition, so we only came 4th there. But I think this has been a great experience for the athlete, Owen Colum, and I think it's had a big impact on him and us in terms of being able to develop this type of strategies and so on. So our ambition now is to take this and make it an easy system so that any students or any, we can have, in 2028, there's going to be another competition in Singapore. It's going to be in Singapore, so hope everybody. Essex should have a team. We should get a lot of UK teams going to that. I think it would be great. And just yesterday, this whole story was told in the New York Times, so that was another good outcome if you want to have a look at that link. It's also got the invasive technology that was used in the 2024 in that, and I don't know if you saw the cybathlon competition, but the invasive or implantable technologies were way ahead of the non-invasive. So it does show the differences. But it's still a complicated system, and what if we could do, just enable the movement of those things in 3 dimensions by decoding the 3-dimensional movement of imagined movement. And so we tried to do this with this technology where we get people to point in 4 different directions, and this is the trajectories of the pointing. And then we ask them to imagine pointing in those 4 directions. Then we try to learn a relationship between the brain response, or basically decode the 3-dimensional coordinates from the brain by trying to match it up to the real trajectories. And we did some stuff with 2D kind of screens and 3D arms on the screens, and it's not very kind of intuitive, and it doesn't give the person a feeling of embodiment. So we wanted to see whether putting a VR headset on would make that better, so you'd have a virtual embodiment of the hand when they point to the different targets. And so we did this as a within subject analysis. We did 10 sessions, so every subject did 5 sessions of 2D and 5 sessions of VR. And this is kind of so you basically 4 seconds, you point and move back in 2 seconds, and then relax. And you can see that there is changes that we could pick up in terms of event-related spectral perturbation. And what we did was we combined multiple windows of event-related spectral perturbation, expected features using convolutional neural networks, combined them temporally using LSTM, and what we ended up with was with a velocity vector that allows us to position the virtual hand in 3D space. That is quite a complex framework, lots of data, lots of parameters. So we use a thing called asynchronous successive halving algorithm, or ASHA, in RayTune, and significantly reduce the time, even though we're doing large global optimization of these systems to try and get them operational. Whenever you start using AI, you have to kind of use Python. So Simulink doesn't really work well with the latest AI models, converting them straight. And sometimes you need TensorFlow and other ones to run the models. You can't just take the weights and apply them. Something that you code it up yourself offline. But this is the kind of the online framework where we do a lot of the pre-processing in Simulink, do the error speeds in Simulink, then send them to Python, and that applies to CNN and LSTM. And then we get real-time feedback in Unity, obviously through the thing. So this is kind of the results there, where you can see there is some reasonable correlations in Z and Y directions or coordinates. But when we look at the 2D, you can see that it's around 60% for 2D, and 65 or more for VR. So we've kind of shown here that definitely VR is beneficial in this scenario, and significantly better than 2D. And therefore, we think it's worth the effort of putting a VR headset on, especially in this thing where you want to have that feedback that kind of gives the user a sense of embodiment and immersion in the task. And I think that's important. We also showed that if we look at brain functional connectivity, that there's differences when we do VR versus the 2D screens, with VR associated with stronger connectivity between sensorimotor regions and frontal executive areas, with links to the motor cortex. And I think this is quite important that there is differences. Now, the only thing is a VR headset is going to change the electrodes a little bit, and so you have to be careful with some of the conclusions you draw whenever you've got 32 channels of EEG and you're doing functional connectivity and so on. But I think this does indicate that people activate brain areas and with that sense of embodiment differently and learn differently. We can also show that the cross correlation of decoded versus target velocity is kind of more aligned when we do three-dimensional spatial feedback compared to the 2D feedback. So it makes kind of sense that you're nearly aligning with the real trajectory whenever you see the virtual arm moving in the real trajectory versus something that's on a 2D screen. We also did a lot of questionnaires to see what really makes what's predictive of performance, and we found that these kind of task-focused, motivational, affective state measures were more predictive or significantly or nearly significantly correlate with performance compared to this kind of contextual experience, workload, and capability states and traits. Interestingly, vividness of visual imagery is completely negatively correlated. Can anybody care to explain that? No? It's probably not that easy, but we didn't do a motor imagery questionnaire, which is unfortunate, but even though we had 32 channels, our BCI kind of focused on 17 that were focused over the motor cortex. So people were doing visual imagery more in this task than they weren't going to perform as well. So that might be that the visual imagers or people were tending to do visual imagery as opposed to kinesthetic motor imagery might have performed worse. So I think every study should measure traits and states so that we can kind of get a better picture and have this metadata alongside all sorts of EEG data so that we can start to stratify different types of users and stuff like that. But I think this idea of different types of feedback is critically important for learning and motor imagery BCIs, and especially three-dimensional control type BCIs. And what we want to do is try and build on that and do much more with different types of feedback, which is yes. And we're looking at this here, which can move. We couldn't find any exoskeletons or robotic kind of wearables that does this three-dimensional movement in 4 directions. But this technology does do that. It kind of moves the arm. It can give you force feedback. It's used in rehabilitation context. And so what we want to really do is show if proprioceptive feedback alongside VR would give you even better experience. So VR versus VR plus proprioceptive. Okay, moving on then. So we've kind of done a similar thing where we want to try and determine if we can decode three-dimensional movements of the limbs. And we just did a very basic stepping task. So the person had to stand and step and return on the spot. And in one group we did self-paced return, and in another group we did a cued return. And yeah, this is kind of the paradigm that was used there, and you can see the differences in the velocities and X, Y, Z kinematics there with the movement. And so whenever we did this, we showed that DL, deep learning, was better than multilinear regression, which is often used in these kind of three-dimensional motion trajectory prediction type BCIs. And we can also show that the decoders aren't too bad either. They're reasonably good across different frequency bands, hitting 80% correlation or higher in some situations. So this is a doable task in terms of decoding lower limb motion trajectory. And there's some of the analysis there where you can see that there's quite good alignment and correlation for some tasks. And again, looking at functional connectivity, there is things that we can learn from this, albeit that we had minimal electrodes in this particular study, which was 16. But we found that the fibular head, so placing the electrodes here was more informative than further down the ankle, and that some directions were easier to decode than others. And so, yeah, the main summary of that was, highest accuracy at the fibular head, dominant EEG contributions are in the sensorimotor areas, frontal involvement in the group 2, which had the cued feet step back. And we only saw significant functional connectivity in the group 2 with this cued step back condition. But it was significant. So yeah, there's things that can be learned about this and what features might be able to be used to improve decoding. Sorry, that's not really needed. So this is what we wanted to do, was to translate that three-dimensional decoding into a lower limb gait rehabilitation technology that allow you to really predict the intended step to a very fine resolution. We didn't get to that in the project, but we did partner with Exobionics and went to California and established the connection that would be needed to inform the gait parameters with their Exobionics lower limb gait exoskeleton. And so here every step is initiated by the brain-computer interface, but it's not three-dimensional decoding. The step is then done by the device. But it's still important in the sense that this was the most steps ever externally commanded in the Exobionics device, because they've got a closed system. So we established this protocol and got it all set up. But I think the important thing is that even in that scenario where you have to engage the brain first and then use that to actuate the device is important in stroke rehabilitation, because it's an active engagement, and it's better than having a passive rehabilitation device where the person doesn't really have to do anything and they're just moving. Or if the person cannot move to initiate the device movement, then if we can detect their intention to move, then so that you get that whole kind of engagement, and I think that's been shown through a number of different, the amount of time and hair tearing I did getting this set up. So there's quite a lot. So the way the device works is it's a left lean. If it's a left lean, then it's a right step. If it's a right lean, it's a left step. And you have to, that was used to synchronize. So once we heard a left lean from the device, then we had to determine, was the person imagining a right or intended a right foot, and if they were, then the device stepped. If they weren't, then it was a delayed step. Lots of control on that. But this idea of being able to have a BCI to improve stroke rehabilitation has been around a while, and there's been lots of evidence to show that BCIs do outperform other assistive rehabilitation technologies. And I think that is really simply because BCIs make the person engage neuroplasticity or the brain first. And I think this is a very important application of BCIs. And there's a window of opportunity that we need to get BCIs into, but also even beyond that as well. And I think that's become apparent. So I'm going to move on now to some of the research that we've been doing in disorders of consciousness. And so I think there's an awareness here among some of you who have been working in this area that this is the kind of the challenge is trying to discriminate when somebody who is completely unaware or unconscious or lacks any conscious to those who have awareness and consciousness. And that can be quite difficult if they don't have a standard behavioral response or can respond to command with a behavioral response. And so there's a lot of misdiagnosis in this scenario, and a lot of the evidence in recent times with neuroimaging and so on is to indicating that there's not that many people who are completely unaware or unconscious, and could potentially be misdiagnosed. And so the standard techniques are to use methods such as the Coma Recovery Scale Revised or the Wessex Head Index measurements, and there's a lot of kind of shortcomings within these tools, but they are the gold standard used in clinical practice, and they do a reasonable job, but they sometimes, especially miss indications of consciousness because the behavioral response is just not there. The person doesn't have motor capability, but they are cognitively intact, or not intact, but yeah, certainly levels of cognition that would allow them to do the task or respond if they could control their motor outputs. And so what we do is similar to what Cruziel done in 2015 or 2013, I think it was, where they ask the person to, every time you hear a beep, imagine that you're lifting your right hand, or every time you hear a beep, try imagine that you're lifting both feet. And we do that over a number of different blocks, so 15 hand, 15 feet. So it's a block design in the first assessment. And if we find that we can discriminate with greater than 70% accuracy and it's above chance in that initial assessment, then we move them on to a feedback session, or a number of feedback sessions in which they get a command left or right, and then they have to modulate the brain activity and listen to the sounds and try to learn to modulate brain activity and improve their ability to control a BCI, basically. And then after about 8 or 9 sessions of that, then we move them on to a Q&A system, which is a closed kind of questions where we sit down with the family member and we get the appropriate yes/no responses to standard questions. We ask the family member to read the questions aloud, and then we record the family member doing that, and then we play the questions back to the participants and ask them to respond by imagining movement left for no, or whatever. And because they've already been involved in 8 sessions where they've got feedback, this task shouldn't be too difficult, or at least they should be understanding the task. And you're gradually introducing more and more complexity into the paradigm over multiple sessions. We also categorize the questions into different categories: biographical awareness, situational awareness, abstract reasoning, numbers and letters. And so the questions kind of follow this thing. We do 40 trials, 40 questions in a run. And the timing is kind of similar to what you see here. So you've always got this kind of standard timing that we use across the different paradigms. So we've done 42 participants in this study to date, plus 2 able-bodied just for comparison, and 14 unresponsive wakefulness syndrome, 17 MCS, 11 locked-in syndrome, 2 able-bodied. Out of the 42 patients that started, 31 moved from assessment through to feedback sessions. So 8 of the 14 UWS moved through. So that means 8 people that are assumed to be unaware and lack consciousness have been able to move to the next round of sessions, and 13 of the 17 MCS. So that's quite an important result in itself. And what we've been able to show then is, if we look at the accuracy of runs, all runs or significant runs, then there is differences between LIS and UWS and MCS when we do motor imagery BCIs, and that's quite clear. There's significant differences between UWS and MCS, but less so when we look at MCS and UWS, and that might be an indication that there is a problem with the score or the indexes that measure these patients. In fact, we're seeing that some UWS are performing better than MCS and so on. So, but it does show that motor imagery could be a good predictor of LIS versus UWS and MCS, where in some cases the people that are LIS are diagnosed with locked-in MCS could actually be LIS. We're also looking at the questions, and we can see that UWS perform better in the Q&A sessions. So there was a significant difference between UWS and MCS during significant runs, and LIS performs better than MCS, but not UWS. And we can see that different participants perform differently in response to some questions and some categories. And albeit it's very early days to say this, but this could be a paradigm that you could look at different levels of cognition or different types of cognition if you can establish enough power in the analysis to look at different types of question and answers and so on. And we also see in this group that there is some improvements over time. You can see there in the first two assessment sessions, you can see very high accuracies, and that is because they are block designs, and often you have to control for that. But you can see that the baseline, always reporting baseline is pre-Q is important, because you can see there, if I reported 80% in session 1, then on the face of it that looks brilliant, but it's only about 15% above chance when we look at the baseline. And again, that is because they're block designs and the assessment runs. But you can see improvements over time, albeit very gradual and very slow, and maybe not representing anything to say that this patient or participant could start using this as a communication channel, but certainly it's promising to see that. And yeah, if we look at the sorry, I'll just get rid of that. So the other paradigm specific differences, if we look across patient groups, and you can see that in feedback, MCS and UWS are kind of similar, but in Q&A, UWS perform better, and this is always performing better than UWS and MCS. So what can we do with this? Well, we want to kind of understand which one was the best. Was it CSR or CRS, WIM, or motor imagery that was the best for predicting outcomes? So we did a multilinear or multinomial logistic regression, looked at balance accuracy. So we did a leave one out cross validation, basically, where we did regression with the CRS, did regression with the DA, did regression with the WIM, and did leave one out to see which one. So this is kind of post hoc analysis on the data, and we found that best group performance was LIST, so we could predict LIST the best. Strongest performance was with MI-BCI, with about 55% accuracy overall, compared to CRS. When we did a further post hoc ensemble analysis, where we try to use a majority vote, we could see that if we combined all three metrics and did a majority vote with probability-based tie breaking, we can improve the predictive accuracy by about 62%. So this is a modest enough improvement, but it's still showing that it's a way of quantifying how accurate these are, and it's really showing that MI-BCI is much better at distinguishing LIST from DoC. I think this is an important result. It is in a couple of preprints going back, but we have a paper. Hopefully, it'll be accepted in a high impact journal soon, and if it's accepted. We also did some functional connectivity analysis with this, and these have to be kind of really taken with a pinch of salt, because it only is 16 channels, and it's not really enough to enable conclusive evidence, but excuse me. So we were able to show that UWS showed thalmofrontal and default mode network, frontal parietal network differences in FC during assessment, and demonstrated differences in auditory frontal integration during training. And yeah, so the most extensive FC differences were in UWS during Q&A. So there is insights you can gather from functional connectivity analysis, but and it really shows that there are differences between groups in terms of their activity and connectivity. 5 minutes, okay. We also see that this is just examples where in the UWS group, it's not very focal at the start during assessment, but as feedback goes on and we get to Q&A, we get a more focal, expected kind of area activation whenever we get to the last few sessions. Same with MCS, so it eventually gets to maybe more focal. These are kind of plots that are based on CSP weights, so where we're actually using the information to decode in the classifier. Whereas in the able body, it's very focal from start to beginning, so that just kind of shows you. And this has also got a little bit more focused earlier on. We also did a kind of pilot with some of the participants in that study where we looked at auditory oddball protocol to see if it correlated with motor imagery. And we did see that, with UWS, decoding accuracy in motor imagery is the lowest, but also latency in the oddball paradigm is the highest. And, so there's an exact anti-correlation that you would expect there. So these two measures might complement each other. Just going to skip on. So again, this is just, there is a lot of potential for this type of technology to have an impact on people's lives, and I think that's the important thing. And this family participated in a survey done by the Nuffield Council on Bioethics, and that was kind of one of the comments from the parents. And so we've got this trial ongoing with multiple hospitals across the UK, and we're hoping to build on this to try and look at what can you do with this type of analysis? What can you do with this type of technology? How can that help clinicians? What is the health economics of being able to do this? Is it cost saving? Does better diagnosis lead to better quality of life? But also, how does it impact on healthcare systems? And we've got a secondary study in Ulster University looking at how the families experience this technology and the lived experience of families when dealing with patients who have locked in. And most of the time we're talking to the families because we go to the patient's home, and there's a variety of insights and stuff that we're looking at there. So I'm not going to go into the PTSD because it's running out of time. But yeah, the big challenges with these technologies is the variability, the non-stationarity, dealing with modulations and signals that are affected by all sorts of scenarios during the day, and that there was very limited data and very limited effort. Like some of them studies are 10 sessions, 12 sessions. There's very few motor imagery studies that go beyond 20 sessions. That's 20 hours. Become a professional at anything, you need a lot more than that. So how can we get the number of hours of participation up without totally wrecking people's heads? And I think that is essential. There's also this human machine learning dilemma. If you're going to try and give people technology in the home, you're going to have to deal with that and try and make sure that you're continually adapting to meet the individual improvements and keep the person motivated. If you're going to use this as a therapeutic device, it's nearly a lifestyle or behavior change that you're needing alongside the technology, because people have to get up, put on a technology, do something for a half an hour a day to have a beneficial effect or whatever it might be. And it's much easier to take a pill than to do that. And that's a big challenge that we need to try to address as well. And I think making technology accessible and easy is one of the ways to do that. And that's why we've set up the NeuroCONCISE and developed this kind of cloud platform and infrastructure that allows us now to collect data on a tablet. Everything's embeddable within a standard headgear, so it's on a flexible substrate. And we've got some good improvements in that technology over the last while. We've developed these electrodes that have the channels in them, so it allows you to direct the gel to the tip of the electrode. So these electrodes can be used dry or wet, but I think if you're going to use them wet, you want to use the minimum amount, and you want to get that gel right to the tip. So I think this works really well. You'd hardly know that the person has gel on, but it's very important, especially even when you're not using legged electrodes. You have to use a lot of gel, and then they're not really, if a person's going to wear it all day for long periods, these things kind of anchor it in the hair and just have that little bit of gel going in, and we've got things like that. And so we're trying to make it a little bit easier and better and less obtrusive than some other technologies. And what we want to try and do is to go beyond the lab and get these technologies into the home so we can get more hours and more people. And I think this is essential that we do this. You know, this 20 participants, 10 hours is absolute torture for us as researchers in the lab, because you have to bring people in and do it every day. And you know, once a PhD does that for their PhD research, then they don't really want to do it again because it's such a torture. So we try and make that easier. And there's a lot of reasons why we can do that, and lots of applications, lots of things happening in the space. You know, the prices are coming down, performance is going up, and it's kind of following that law of accelerated returns as predicted by Gerb Schilk way back. And there's a lot of activity in the UK that I think, you know, we can really take a positive kind of approach now to doing neurotechnology, although a lot of the implantable stuff is getting a lot of attention at the minute. But I think non-invasive BCIs have a huge role to play in developing neurotechnology ecosystems long before implantables will become ready to use and safe to use. So I think we need to develop the whole ecosystem around neurotech, non-invasive neurotech first. And that's why we've set up the Bath Institute for the Augmented Human, where we're not only doing neurotechnology, but bringing together the various technologies and expertises across multiple different faculties and disciplines, not only focusing on health applications, but in sport, defence, workforce, and not only focusing on fundamental research, but trying to drive that through this innovation ecosystem so that we can get technologies through regulatory pathways, get more trials done. And if the academic only wants to take it to this point where it's really good research, they should have an idea and support to bring it beyond that. And that's what we want to set up. And we've got a core team that's really focused on enabling that. Okay, that's me. Oh, just one thing. We have access to that technology if you're an interested in gamer, but we're also delivering 25 headsets to 25 people in their home every month for all 12 months in 2026. And the commitment is 21 hours of utilization anytime you want in your own home. And you'll have a tablet and a device. And we'll probably have some teething problems. So it would be good to get some BCI experienced people being our first participants, and then we'll go to less experienced people. But if you're interested, how deep there, HSS 70 at Bath, or you just get in contact with me, and we'll ship you a headset, and there'll be a few states and traits questionnaires during the study. And yeah, you can give us loads of critique and feedback if it goes wrong, right? Okay, thank you very much. Hope I didn't run over too much.
All right, so thank you very much, Damien, for this very interesting talk. Before we go to questions, just to say to the people in the Zoom room, whoever wants to ask a question, please write it in the chat, and I will take care to transfer it here. It was just the easiest way to get audio in the room. And if the room has any questions, please, it's time to fire. In the meantime, maybe I have one that I've been thinking. Okay. Since people don't know, you're here also in the pretext of a Viva that was about disorders of consciousness.
Yeah.
So this is a topic I just discussed with Damien also before. Can you maybe go to the slide where you're comparing the accuracy of the different indications, UWS, MCS, and so on? Because I think there is something that is also consistent with our data, which is that there
was an easier way to do this, but sometimes it messes up.
Yeah, exactly. Yeah, these kind of plots. So what we see is, and we also see it in our data, the healthy controls and the people we know are aware, like the locked-in person, they do much better than the UWS and the MCS. And the question is, however, how much does this help us? Because in the end, the critical distinction we are called to do with the EEG technology is to discriminate exactly between what people think with CRSR and the other clinical scales is unresponsive wakefulness syndrome or minimally conscious state. And we're just trying to see if somebody that is considered by the clinical scales unaware, whether in fact is aware. So for instance, you would expect here, if there is information in this very small critical region that is very tough to discriminate, you would expect the MCS to be at least a little bit higher. And we don't really see that, and we don't see it in our data either.
Yeah,
so
but
isn't this a problem?
not really, because that kind of points to there is a problem with the CRS, right? You know, that there isn't much difference between UWS and MCS, perhaps, right? That, you know, just bear in mind the results here are on significant runs, right? Or you've got all runs and you've got significant runs, but it's also on runs that have come through, you know, assessments and basically people that are not able to pass the assessment don't make it through, right? So they haven't been able to modulate significantly in the first session, and in the assessment runs, which are block runs, which I showed, and like in earlier studies or in earlier kind of analyses of this data where we had less in these groups and we were seeing slightly greater MCS, and our kind of conclusion was, right, this is discriminating better, right? Or at least it's giving us, but now when we got the whole thing and we're like, oh no, it's not giving us the same story. But it does give it an interesting story in that, like, there may not be, when you do a movement independent assessment, there may not be the same differences. But I have another slide. I don't know if I've deleted it out of this. Deleted it. Did I? Oh yeah, this one here. You know, this was an earlier kind of summary, and it's not including all the data. But you can see the difference in the scores here, right? And here you've got no differences. Does that mean that the BCI is wrong, or does that mean that this is wrong, right?
And that is maybe my second question, if I may, because it's even more critical. And it is the lack of ground truth. So we are developing neurotechnology to solve a problem, which is to correct the clinical scores, but we have no ground truth. So any method we develop, we have nothing firm and
that is a challenge.
Reliable to. So how do we go out with this data? Because I don't have the answer. I'm having a.
Look, we put a lot of effort into clearly establishing that it's a significant modulation, right? So it's, you've got your baseline versus peak, you've got your permutation test, and you've got, you know, proper statistics to look at the differences there. And once you're showing that that's not happening by chance, then that patient, to me, is not UWS or MCS, even though behaviorally they look like that because they can't move to communicate. So to me, this is wrong, and this is more right in terms of showing the response of the patients. How you kind of get the ground truth is difficult, but you know, I think there is work now on
it. It's a good case where you have a lot of hits, and especially if you do multiple sessions and the patient.
Yeah.
But then there is the bad case, and the main thing we're trying to correct with this is the false negatives, which is people that are aware, but we cannot detect it with the clinical scores. And then if they seem below chance level, also with the EEG, what do we do then? We tell, okay, the person is doesn't have awareness.
Well, like we would never say that, you know, to anybody, right? But we would just, like, and there are people that didn't make it through on the first stages, right? And we would just, some of those people had uncontrollable movements, right? And or some of them seemed to just be asleep and they just wouldn't wake up. And you know, so there's different reasons. It's not necessarily that they don't have cognition, but I think it's clear that if you do see significant modulations, then the person has a level of command following. And if they're even in this condition and they're producing significant sensorimotor activation, then they're definitely not UWS as described. they might be, have cognitive motor dissociation or a CMP. But I think that's quite important, and I think there's a lot more to be done with this type of Q&A and doing more sessions. And I think we're your paradigm didn't have real-time feedback, and I think if I give a student a BCI for 3 sessions and don't give them any feedback, they'll probably look like they're UWS, because it's not so boring, right? So I think that's an important thing, to get the feedback in there early. And we do task versus task, but we still have a resting state, whereas your paradigm had task versus rest, and still had a rest pre-cue. And so there's differences there, but I think they're all they're all experiments. It's good to try them out, but I think the real-time stuff is the way to go. However, this is difficult, right? This is a researcher going around, spending 3 weeks in a location. Hopefully we have 3 patients in that location, and they can get 3 done whilst they stay in that hotel. Otherwise, it costs too much to go back. So with the neurotechnology that we have now, we're hoping to be able to have a tablet, that's usable by the carer, and then we can collect more data and get more of those. And we have a headphones, a tablet, and an easy to use headset, and it can be left there with the patient. It's cost effective enough to do that. Yeah, I think that's the mission.
Thank you. Are there any more questions?
No, I want just to add my opinion to this debate about the ground truth. So I think we should shift from just trying to predict the CRC to the prognosis, because these people stay 2, 3, 4 years. So what is important is to understand what is the most likely outcome in 3, 4 years. If we don't start to collect longitudinal data, and I don't know how much sense has just to predict this if we don't have the outcome in a few years. Also because there are many countries very religious, like Italy, or as tradition, they keep people independently in a bed for 3, 4, 5 years, and they give all the care possible. So they don't kill them in most of the countries. So I think this should be the shift.
Last year pointing this out, that you need more sessions to make at least a little bit more reliable inferences. I think you have a question.
But I think it's important that we determine what are the benefits of what we know now, and what do we need to produce benefits. And that, firstly, it's for the family and the patient, but also the clinicians that are, if they had these tools, what would they do differently? Would it save costs? Would it reduce, burden on the healthcare systems? You really don't know until you put something like this in a clinical unit doing diagnosis. When we pitched NeuroCONCISE a few years ago, it was around disorders of consciousness, and then eventually the investor says it's too small. It's a great thing, but it's we don't know what the business model is there, right? But we had the thing, right? If we could move people from acute intensive care beds into brain injury units faster by giving better diagnosis, and then establishing communication channels faster in the brain injury unit, and then moving them to the home or back to the care home, each one of those beds costs less and less as you. So our idea was, right, let's do that. And then one of the guys says, when you just fill them beds again, what happens? And I was like, well, yeah, that's all right. But he says there's that much of a backlog for beds like that you're not going to save any money. That was one of the things. But then we realized, in a brain injury unit, it's not just about diagnosis. It's about, is there a bed for them somewhere else? Can they communicate? What other healthcare needs? What assistive technology? So there's a whole kind of ecosystem thing that needs to be figured out to determine what are the benefits of doing this. But I think therapeutic and engage in neuroplasticity, and there could be benefits for the patient in terms of recovery by getting more stimulation. And I think just as a therapeutic technology, it could be beneficial as well. But we're going to keep working on this for sure, and see where it takes us.
Yeah. Hi, Damien.
How's it going?
So first of all, great to see the new paradigms you have developed with VR and all for motor imagery, BCI,
Yeah.
and its use for rehabilitation. But my question is that, like, when these paradigms comes for like randomized controlled trials with usual care, most of the studies has resulted in negative, I mean, like equal outcome as compared to the usual care. So this getting significantly better result than usual care using the motor imagery BCI paradigms.
For
Is
you talking
really-
about stroke
Stroke
rehabilitation?
rehabilitation, yeah. So I was thinking about what could be the right use case of these technologies, because the clinicians are not really very interested unless they see significant benefit of out of these technologies. So
Yeah, I suppose there's things around. There's neurofeedback studies done in stroke, mental health, pain, and they're small enough, but they are providing indicative evidence of benefits. And I think in stroke it's more clear cut that there is a benefit, right? But I'm not sure what study you're referred to.
I mean, yes, like patients recover. I mean, like when you compare the baseline and the post-intervention motor outcomes, there are significant improvements.
Yeah.
But when you compare it to the usual care, like it is often seen that the improvements are the same. Like you can't differentiate between the two groups.
Yeah, like what's the point then? You're saying, right? But I thought there was more evidence for stroke rehabilitation with this tech than there is for the other ones. But if there's not, is it to do with the paradigm? If you're just giving somebody, visual feedback on the screen and it's not motivational, they're not getting a good feeling for control, and there's not, good enough AI on there to kind of keep the person motivated, then maybe it's not a great intervention, and maybe that's why the thing failed. If it's closed loop FES, and it's very basic, and it's not very accurate, it really depends. But I think G-Tech and their gems are certainly showing better outcomes in that. Like when I see that, I don't know, it's not published, but they seem to be promoting it as a good closed loop FES. So I think doing those large randomized controlled trials are very, very difficult, especially if it's managed by researchers and everything has to be done down to the T. So I think getting these things accessible in the home with a cloud edge kind of platform and enabling people to do it daily without dragging them into the lab, or I think that's where we can get the bigger numbers. I don't think there's any study that's got big enough numbers to really say this, because there's a lot of different variations on what happens, and what types of lesions a stroke survivor has. And, you merely need to stratify the population so that you've got different types of strokes, and then see which one has more efficacy can be demonstrated depending on what type of stroke a person has, rather than clumping everybody together. And we just got an EU grant that's going to look at some of that activity, and better prognosis for better kind of care pathways based on the person's kind of prognosis.
And last of all, I want to ask, like, what do you think the major challenges for adoption of these technologies in the clinical setting, especially if I talk about motor imagery BCI for stroke rehab?
Yeah, it's a good question. It's a lot to do with Well, first of all, training the clinicians to use these and deploy these technologies and offer them to patients. It's about the business model or the health economics, trying to understand, well, how is this technology prescribed, and how does this be used by or clinicians or consultants in rehabilitation medicine. Like, I've spent some time in hospitals, doing trials and doing even when my wife had a stroke, and I think it was the occupational therapist would come every day and put an FES passively on. It kind of buzzed the legs, but they didn't really know how to use it, and they didn't really, they just went away and came back, and hopefully it was given enough stimulus. So there wasn't really a very kind of structured way of doing it, and to do it with BCI would be even more difficult because they don't have the clue or the knowledge, and so a lot of training is necessary. But and then the patients would learn how to use it and then go home and use it every day at home and get those repetitions up, because I truly believe in stroke rehabilitation. It is, if you have any chance of recovering function, you have to get more and more repetitions, and they don't do half a quarter or even a percentage enough repetitions. And then once it's they're out of the hospital, it's kind of like we don't do it anymore, right? And so if you can keep people going on it, and it could take years. Like, my wife had no movement; she couldn't open her hands, and it was very small movements. And I was surprised about a year or two ago. I seen her opening it much better than anything had happened in the first year. But I didn't really pay attention to it after that. But so and she did a lot of repetitions because I was making her do them. So it might have, the effects might be seen a lot later than what we're measuring as well.
I guess we can wrap it up for today. Also, our speaker has a train to catch, and we cannot refund him. So, Damien, once again, thank you for honoring us with your presence. And the rest of you, stay tuned. Next month, we have Marie-Constance Corsi from Sorbonne University. So, until next time, thanks a lot.
Thanks, everyone. Thank you.